I'm back on. I think it's timing out. I think is what it's doing. At 20 minutes, I think it times out.
But yeah, this is an example of pitting, which would have started from just one little spot at the top and then works its way down, progressing into the structure that is made of that steel. Appearance of the actual corrosion due to chlorine, I wanted to get a little bit closer. So this one is like a microscopic view of how the transgranulate cracks kind of go down in steel. That's the stress corrosion cracking we were talking about. And over here is, I can't even really see that. That's a terrible picture anyway. That is another example of it, but it's just bad. Standard test methods for pitting and crevice corrosion resistance of, Standard test methods for pitting and crevice corrosion resistance of stainless steels and related alloys by the use of ferric chloride solutions are outlined in ASTM G48. Ooh, that was long. All right. The testing method actually is the wet cannon method. That is typically used, and we went over that in the black book as well quite a bit in Intro to Corrosion. Control methods. Corrosion inhibitors are the primary means of inhibiting chloride corrosion. So if you can bind up those ions with other just throwaway chemicals that you're using to bind them, they will not be able to use their charges to damage the structure and contact. That is, chemical elements added to solution to passivate with chloride ions present, therefore preventing corrosion of metallic features contact with chlorides, because they will no longer be chlorides once you passivate them. Typical environments for caustic embrittlement. Caustic embrittlement is a result of a buildup of caustic soda in boilers. And I looked up a lot on this because this is where I started, and I found very little on anything but boilers. Boilers seem to be the primary victims of caustic embrittlement, and that's because they use this thing called caustic soda, and I'll explain that as I go. But caustic embrittlement is almost exclusive to boilers, in which caustic soda or lye is added to water to prevent scaling of the boiler pipes, and that's that corrosion product that we were explaining earlier. But in order to prevent it, they put that in there, and then it builds up over time in the small cracks and areas of the boiler, and under such extreme heat and pressure and velocity often, as we were discussing earlier, it is subject to becoming extremely brittle extremely quickly, and that's just not good when you have something that hot and that pressurized. That's typically in an urban environment, or an HCA, I guess you would call it, because the boiler exploding is never good. Any steel reinforcing materials exposed to chlorides, they're susceptible to caustic embrittlement as well. Possible vulnerabilities: rebar. Structural supporting steel is vulnerable to chloride attack, and any steel exposed to a liquid environment is at risk of chloride. Excuse me. Okay. Yes. Temperature, as far as affecting factors go. Temperature, the higher temperature in a boiler is, the high temperature a boiler is under contributed to the high rate of evaporation of water, thus leaving behind accumulating levels of caustic soda. That's what I was explaining earlier. It's such high temperatures, high heat, high pressure, bad times. Pressure increases temperature, therefore increasing production of caustic soda. This is like those areas I was telling you about. Like, it's not necessarily even, it's like a 90, kind of 30 or something. But right there, the erosion corrosion played a part in it as well. But the caustic soda was able to actually completely through that part of the metal. I'm not sure that whole piece cracked out at once. I'm pretty sure it was just super thin, and then something happened to it, and it poked right through. These are another two examples of the brittleness resulting from that corrosion cell. The corrosion cell mechanism for caustic embrittlement is a specific form of SCC and occurs between 200 degrees Celsius and 250 degrees Celsius as a result of concentrated hydroxide. If lye, caustic soda, is to be used in the softening of water to be heated in a boiler, sodium phosphate may be used instead to avoid the specific form of SCC. This is the control method.
Hydrogen sulfide. We've got a picture over here. We'll call the sticky gas corrosion. basically shows here what is H2S. It's a naturally occurring chemical produced by bacteria in a decomposing organic material. When I looked up in a lot of these places, it was used or is caused and is affected in a lot of the water treatment plants or waste treatment plants. And what they do is they basically start on the inside where the hydrogen builds up and combines with the sulfide and eats away at the material. Holding tanks, a lot of them, if they're lined, are made out of cement, is one of the biggest corrosion factors that causes it to fail. Here you can see the inside of the pipe where it's eating away at the cement and causing it to collapse. But also if there's a ventilated area where there's grading over it, where they might dump chemicals or just checking it to see how the product's flowing, the corrosion can come up and also eat away at the metal. A lot of the vulnerabilities is, or to keep it from happening, is monitor the gas. I got what they call CGAs. I've installed a lot of them in the chemical plants. It detects different types of gas, all depending on what kind of monitor you put up. Keep the dissolved oxygen in whatever the liquid may be below 0.3 milligrams per liter. And keep the H2S levels below 5 parts per million, or increase the concrete pH level to 4 or greater. That will keep the H2S from attacking the cement. Sulfides affecting factors, low levels of dissolved oxygen. If you put something that will keep the oxygen in the liquid of whatever's processed or passed through the piping or the lining, it will help keep it down. Generation of sulfides released of H2S, moisture in the material. If you can try to keep a coating on the cement inside where it flows, or if it's a tank, that will cut down on it. And materials subject to sulfur acid attack, which we go back to concrete, is a lot of the tanks or linings that they have in water treatment plants, or more particularly the wastewater treatment plants. Here it shows basically what happens, the corrosion cell acid attacks and chemicals. It shows how as the H2S rises and it's dissolved out of the liquid and the material, here it comes up and it attacks the top of the cement pipe and causing the location of the oxidation of the bacteria to grow and eat away at the cement. And here we show another one, how if you've ever seen large culverts that go on a road and they get a cavity or a sinkhole, it shows how the water level stays in the pipe, and as it eats away, the cement starts to corrode and deteriorate to where it eventually just causes the whole thing to cave in. Some more visual or appearances of it, and a lot of times they'll try to put in plants that I've worked in, they'll put the H2S monitor gas, say they're using it in this area and there's particulates or chances of a leak, they try to tell you to stay out of that area. Some of the standards out of the day store for that was NACE 97392, which is basically relates to a coating that you can put around the cement or on the cement to help keep the hydrogen from eating away at the concrete, or NACE MR 0175. And now we come to hypochlorites, OCl. It's basically the salts of corrosion also, which everybody's had some kind of salt in their presentation showing that it's horrible. Keep back the salt if you can. Typical environments, water plants, wastewater plants. Now one area that it does show up a lot is in kitchens and restaurants and holding tanks, where they make the tanks out of stainless steel or stainless steel equipment in the kitchens. And it takes a lot to keep them clean and keep the hypochlorite off of them, to keep from attacking the stainless steel that they use to keep everything else from attacking whatever metal they use. And this one shows another stainless steel, how the hypochlorite can attack the stainless steel, or if it's if it leaks out in a liquid form, and to show how it attacks the cement floor here, and has basically caused the whole floor to become brittle, and they have to scrape up and put new coatings on it to keep it from getting any worse. Possible vulnerabilities: any stainless steel in contact with the high sodium content, or concrete in a high salt area bridge, like say a bridge near an ocean spray. If it goes over brackish water or partial salt water, you get a lot of constant chlorine spray on it, which causes, like he sampled how the chlorines get into the cement and into the steel of the rebar and causes it to flake off. Some of the affecting factors, it seems to be in basically everything. High temperature and exchangers, flow rate, hitting the back of 90s like he showed in his pictures, how the velocity as it hits, that salts are just like an abrasive also, and causes the back of the 90s to just constantly wear down. And in contact with, impact with whether of sea spray or on bridges like I explained earlier. Here we show the corrosion cell mechanism, how bad the hypochlorite can combine with almost anything, and attack the coating on stainless steel, which allows sodium or other chemicals to attack the steel itself once it wears off any patina or corrosion that it protects itself from. But once the hypochlorite wears away at that, it allows other things to attack the steel itself. And here we have some visual appearances. This is in the bottom of a pot where they constantly boil water for cleaning things. Here we have an example of where the bridge, it shows where salt water or any kind of hypochlorite in the environment will seep through the cement and cause the rebar to swell. And that one over there, like many people showed, an exchanging tubing, where it has just built up and eat up on the ends of it, where they exchange the flow rate back in and out of the pipes from one another. And then once again in the NACE store, it was, for this one, it was NACE 08524, which is a resin coating for sodium hypochlorites in tanks. If they're holding a bunch of liquid in a tank that is susceptible to this type of attack, this is coated with this type of resin here, and it'll cut back on the corrosion of the inside of the tank. And then we come to oxygen. What can we say about it? We can't get rid of it. We'd all die. There's nothing else to really do. You can get oxygenators to cut back on it, and everybody needs it, yet it is one of the most largest types that really bonds to anything and everything that causes most of our corrosion. Oxygen, typical environment, well, it's everywhere. In the air, water, soil, solid rocks, in everything. You couldn't really get rid of it unless you try to just pacify a type of material by taking it out of one small area, causing a vacuum or something like that, or a deaerator to try to remove the oxygen from the liquid. Materials, once again, it attacks everything. There's nothing that it doesn't attack, nothing that it hinders, nothing that it helps. You just can't cut back on it. Anything that oxygen can bond to or consume, it's there. Possible vulnerabilities is saturated oxygen systems, which could be a closed boiler system, boiler corrosion, which would be the heated system over the oxygenated areas. METL, which will somebody else explain, for the microbiological influence of corrosion. More oxygen, more bacteria, more growth, more corrosion. It all goes back to that oxygen. Everything has to have oxygen to feed. Now, some of the visual appearance, it shows here how the O2 can cause a film buildup and cause blistering, which could lead to, if it cracks, to the pitting. Even underwater, you've got some dissolved, there's some water, oxygen in the water, and even it shows the diver pulling up a piece of steel that has corroded, not as a great of a rate as if it was sitting on land, but in salt water, there's more salt, there's more oxygen, and it still corrodes. Another one, we go back to the concrete, as far as how much, too much oxygen can cause the pH to lower, which it still causes the effect of, on the cement, where the rebar can start to rust from the inside out, which causes the flaking of the cement and leads to more corrosion. No oxygen, no life. We've got to have the oxygen, we just got to learn to cut it out where we can. And there's our works cited areas.